Uh, okay. So if I think you already familiar with the video recording about the entry, right? So the entry is somehow that we can manipulate, so that I think you probably heard about the situation like if we have let's say if we are talking about autonomous driving, and if we use deep learning, right? You probably heard about, let's say we already heard about some accident used by autonomous driving, right? So given some situation, there's an accident, right? Then if you are the if you are the person who built the model before, right, for that autonomous driving, so what you are going to do to erase that kind of accident in the future? So the answer is not that easy, right? Because back end that you know that you train a deep learning model, right? Then the deep learning model gives us some kind of result, like accident, which is not allowed. But you don't know how to undo the thing, right? So you don't know how to make the model don't behave like this in the future. It's not that easy, okay? So some naive method would be like, okay, and for deep learning, right? For autonomous driving, maybe they try some similar uh, see that for the driver, I mean for the car to check again and again, so that they can try to give them the right way to avoid some kind of accident, right? Okay, but I think there must be tons of those data, right, required, right? Because the model has been changed. So if you want to change the model behavior, right, must be you add more and more, a lot of more data, so that you can undo whatever has been done before, right? Okay. Besides, you don't know. That will be enough, right? Okay. You need to try that test for so many times. So, but it's not for the entry. But the entry is something that you know why you get yes and why you get no. So you can manipulate. You can manipulate to make the result, right? Okay. But on the other hand, you know that to be a lot of things that we say, oh, the entry is not so good, right? Can you name anything that the entry is not so good? Can you name anything? Like, for instance, how you can say, okay, for instance, this tree is not good enough, right? So then we talk about we based on I mean there'll be more than just one algorithm, right? But one here we talk about the ID3, right? ID3 algorithm is that we always start from the root to find then we want to find what could be the most salient attributes. Okay, so we start from, for instance, the ones we do it step by step, right? So if we maybe I should try it like this way, right? So like they can see. Okay, so if we start from the root, right? So we want to search for what would be the best attribute, right? Okay, after we decide what would be the best attribute, then sort all the data according to different branch, right? Then we do it again and again. So that's what we can call type greedy algorithm, right? So given this algorithm, okay, given this algorithm, suppose the tree that we are is like this, right? So one thing we can say, is not good enough just because it's greedy algorithm. So it doesn't guarantee that the result is optimal, right? Okay. Another way to say it is that the model consider the attribute not in the same, uh, doesn't consider the attribute simultaneously. So it's kind of like they don't consider the attribute interaction between attributes. Okay, so which means that if there's any nonlinear interactions between attributes, the gene tree cannot easily deal with that. When I say nonlinear, meaning the other way is linear. Right? Linear is like, okay, everything can be addictive, right? So we can deal with outlook, right? So when the outlook is not good enough, we try something else. We add one, eventually. Okay, so the greedy algorithm, in a sense, it says that everything is independent. You get that? So when we know that the outlook is the most important attribute, right? Then later we say, right, what condition are okay, the data is something, the humidity is, etc. Right? So we kind of have the conditional independence built in, okay, in the assumption. Okay, so everything is like this one condition independent outlook result and what is the best attribute. The condition on all this, what is the best? Okay, no good, right? Because they never consider all the attributes at the same time. Okay, yeah, so that's the thing. That's the weakness about the tree, right? And also, it's not that easy to overcome this kind of weakness. Okay, yeah. So, I think you can try something like maybe you can deal with backtrack, deal with backtracking, so that we can say, oh, can we use can we erase that we just decided, right? To make sure that maybe we try some other approach, some other ones that maybe we already decide. Humidity is the one, right? Maybe we can try to change over to be like some other attribute. Okay, yeah. So that's something we can check, right? But you need to make sure that if we allow backtrack, right, this can be done like a back and forth. So which means that in some sense that maybe it takes longer time and sometimes people never end, right? So that's not so good. Okay. So I think we finished this one, right? Yeah, I think we can start from this one. Okay, we can continue to discuss. Okay, first of all, just because we already talked about the hypothesis space and hypothesis, right? So for the game tree, we know the hypothesis space is super big. How big? It will never be any hypothesis is outside this hypothesis space. Okay, so the hypothesis space is what? Is including everything. Okay, including everything, right? So if you have any kind of hypothesis and true concept that we want to learn, it must be learned by the tree. But of course, the tree, you cannot guarantee the tree is kind of very small, right? Be very big, etc. Right? Okay, which means that we don't know what would be the generalization of our sense. So, of course, we will talk about its robust to noisy data compared to, let's say, before now, for the rectangle, we don't really talk about noisy data, right? I mean, how to deal with noisy data, right? But here, that's just because statistically, we don't have to really make sure that, for instance, if we come to this some region, right? So if the majority belongs to negative, then we just say negative, right? Because we don't have to really say, oh, 100% has to be negative, right? So statistically, we can say it's robust, right? Okay. So usually, you for the empirical case, you will just try, okay, for here, right? It is smaller than some number of data, right? Then we can start. And also, if you think the data contains the majority greater than some percentage, then we stop, right? It's up to our choice, right? It could be like 80% or 90%. If you are not satisfied, then you try further branch, right? So yeah, and if you try further branch, that means that we can continue to decrease like the training accuracy, training error to decrease, right? But we don't know. We need to make sure that the validation is also the same. Yep. Okay. So what's the bias? Inductive bias here. The inductive bias here, they prefer shorter tree rather than longer tree. Why? Because given whatever data that we have, if we can line the tree, feed the data well, then what? Then stop. Right? We will not go any longer with more depths, right? So that means what? That means whatever good enough that we stop, right? That would be small tree, right? Who knows that the truth or to deal with the truth, maybe we need longer tree, right? Okay, yep. So I mean that's different from rectangle, right? Rectangle is we already decide the complexity. You got that? Okay. It's different from, I mean, something similar could be like, okay, if we talk about the rectangle case, right? Okay. If we think the classification is not 100%, we make it, we add more and more parameters, right? Okay, make it to be more complicated rectangle. It's not rectangle anymore. It's in some other shape, right? Okay, yeah. So, and also, just because we use information gain, right? So, whatever chosen by the information gain will be the one that we prefer. Okay, so, and we talk about Occam's razor, right? Occam's razor is that, okay, whenever we don't have enough confidence or evidence to say why do we prefer short hypothesis, short meaning the small, in this case, smaller tree, right? So why the smaller tree is better to use? Why? I mean, we must have some kind of argument here, right? So a few things like this, right? First of all, smaller tree means more efficient in the training and in testing, right? So why not use smaller tree, right? And on the other hand, a smaller tree, when we have a match to the data, it must be unlikely to be coincident, right? Must be, oh, could be that somehow maybe we found the truth already, right? Okay, and on the other hand, longer tree, right, always can feed the data. Even long enough tree, right, we can feed any kind of data. So besides, there will be more than just one tree that we can feed one data if we have longer tree, right? But we don't have so many short trees, right? So once that we found a short tree that match our data, it's more likely that will be the model that we want. Yep. So that's on the other hand, also people say, oh, how can we use Occam's razor just because we are not so sure, right? So one thing very easily that we can say is not so solid is that we don't know how to do the coding, right? We say longer tree or shorter tree, right? So, but how to define longer tree and shorter tree, right? Either we want to define based on the depth or based on the number of nodes, right? It's not the only definition that we can try, right? So there's no clear answer to say why we can define shorter tree, longer tree this way or that way, right? So that's something that we don't feel comfortable with. So, so that's the overfitting. Overfitting, if we compare, I mean, we talked about overfitting last week, right? So here is a clear definition, right? So when we have two hypotheses, right? Okay, then if we say for the training, the arrow is like in this direction, right? Then, but the testing is the other way around. So the testing is the other way around. Then we say that's overfitting, right? So we say that's overfitting. So yeah, so usually we're going to see this kind of curve. Okay, so when we say okay, yeah, here is accuracy, right? So if it for the training data, accuracy continue to grow. Eventually there will be 100%. Okay, for sure, because we just said that the hypothesis space is big enough to cover all kinds of hypotheses, right? On the other hand, we are going to say what? Okay, for the test data, right? So after a certain moment, it will drop, right? Because we think that after that moment, maybe we feel like the model is complicated enough, so that we should, complicated enough is in a relative sense, right? Because we say the data is that complex, right? So maybe we should stop there, right? If we continue to grow the tree, then usually the result will be worse. Yeah, so that's where we have the overfitting. Okay, so we can use this to avoid overfitting, such as that we can try to, other than minimize the misclassification number of misclassification, we also try to avoid long trees, right? We try to make sure the tree is not too big. Okay, so how to, okay, so now that's the second part actually. So we want to talk several variants, and also we want to talk about when we deal with real data, some strategies, some then maybe we can try. Okay, so one is pruning. Pruning means what? Pruning means that we can try smaller model rather than longer model, right? Okay, a smaller model rather than a bigger model, right? So before now we try, let's say, if we consider the number of data, let's say for each of the small subregion, right, down to the bottom, and if we think okay, the number of data is too small, right, then we stop. Usually, we call pre-pruning. Pre-pruning, okay. Pre-pruning, okay. Yeah, pre-pruning. So there'll be several strategies other than this pruning. Okay, so which means that one thing we can try is the post pruning. Okay, pre pruning means that okay, so we continue to grow the tree, right? Okay, after a certain moment, then we stop. So that's pre pruning. Post pruning means that we go all the way. Then we try to shrink the tree to see maybe any other moment, right? So if we think that the test accuracy is maximum, then we stop. Okay. Yeah, so how to do the post pruning? There'll be here we introduce rule based, right? Rule based post pruning. So rule based post pruning is that first of all we make the model be what? Be rules. Okay. So how to make rules? We already uh, discussed that before, right? Such like this, right? For this one, we can say there'll be several rules, right? Okay. I think we can also, on the other hand, we can also stick with the positive and like all others to be negative. That's also okay, right? Yeah. So there'll be many like technical issue here. Okay, very like subtle issue here. If we really want to use these rules, okay, for instance, if we care about efficiency, right? If we want to use the tree for some situation like, for instance, in computer networks, right? We want to make the incoming traffic to be benign or malicious, right? So that will be very painful job, right? It's a very like high intensive job, right? Okay, because the traffic is goes very fast, right? So tons of data coming, right? So we have to very quickly make the judgment. Otherwise, some computer inside this network will feel like it will be something uncomfortable, right? Very slow. So in this case, we have to decide the rule, okay, by checking the ordering, okay, carefully, right? Okay, such as between rule 1, 2, 3, 4, 5. So which one should be the most important one? That's not that easy to make the decision. Okay, yeah. So you roughly speaking, we can say if some of the rule, right, covers let's say 80% of the data, more percentage, right? Then we should what? We should let the rule goes earlier, right? We check the rules at the very beginning, right? Then move on to some other minor rules, more like exceptional, right? Okay. Okay. So that's how to convert the tree to be rules. Okay. Okay. Now that if we want to make it to be like smaller model, right? How to deal with that? How to do that? Basically there'll be some strategy like this, right? So for each of the rule, it's uh, like one term combined with another term, right? Okay, yeah. Then we compute the intersection, right? So we can try to see if some of the term can be removed without giving us a lot of trouble. For instance, uh, we know that outlook looks like very important, right? But for some branch, so for some task, could be outlook is not so important. Who knows, right? So maybe we can, for instance, if we focus on the rule 3, right? We can take term to say, oh, if we remove this term, outlook equal to overcast, right? Or maybe then this one. This one, how about rule 5, right? So outlook equal to red, right? Then if we remove this one means what? Means that if the wind is weak, then we say yes. So we don't care about the outlook, right? Okay, so we can try this to see if the result will be better or worse, right? So if the result is, usually the result is always what? Worse, right? But can we confirm that the result is not too bad, right? If it's just a little worse, maybe we're going to accept that, right? Why? Because we are talking about why? Because we are talking about we want to minimize these two things at the same time, right? If this one goes higher, just a little bit, right? But we can make sure that the tree size goes smaller, a lot smaller, or maybe the rule become smaller, right? Then we can, I think we can say it's a better choice, right? Okay. Yeah. So that's the rule-based post-pruning. Okay. So we can take for each of the term, right, randomly, or maybe we try them all to remove one by one to see the rest can still give us a good result. If the answer is yes, then we continue to do more and more removal. Yeah, until we feel enough, right? Okay. So that's a post pruning, one of the post pruning. Any questions? So another topic now is like, okay, if we focus okay, continuous value, right? If we do have continuous value, so how to build a tree, right? How to build a tree. So here we have something to say. Suppose the one of the attribute is temperature, right? So the temperature, how to how to deal with temperature, right? So maybe other than saying like okay, like a categorical data, right? We need to provide the threshold, one of the threshold, right? Or the cut point, right? So we are going to say, okay, for instance, the temperature above this value or less than this value, right? We are going to create two branches, right? Or maybe we have more and more cut points, right? Okay. To be what? Can we? Yeah, I think. So, so what I'm saying is that we are going to have, let's say, if the temperature, right? Okay, if less than some value, right? Okay, greater than some value, right? So we can create two branch, right? Okay, we can even do more than that, right? Like, right. This one is for the binary split, right? So we can try all, like using, right? There's a theory saying that okay, trying binary split will be good enough. So maybe we just focus on binary split. So if we talk about binary split, right, then if we consider this case, we're going to say something, right? So given this case, can we say how to decide the cut point? Okay, yeah. So think about the temperature is one of the attributes, right? So suppose given several values, right? Then that's the result. So what we are going to say? What we are going to say? How to decide the best cut point? Can you say anything? How to decide the cut point? Okay, or maybe based on your intuition, right? Where that we should decide our cut point? Can you say? Can you say something? Maybe we can call out, right? Yeah, if you are join remotely, you can also say something. Yeah. So where could be the cut point? Where could be the cut point? You think that could be a good cut point, right? Where? Maybe right here, right? And also here. Okay. Yeah. So based on this paper, right? If we stick with the information gain, if we stick with the information gain to decide what could be the best attribute, right? Okay. Then here is like a decide the best attribute, also the best cut point, right? Which cut point will give us? Once suppose that we already agree the temperature will be the attribute to choose, right? Based on information gain. Then the next question is, what couple will give us the best information gain? Okay, so based on this paper, the couple right here and the couple right here will give us the best information gain. Okay, they prove that. Yeah. So which means that if we still use the same information gain, right? Okay. So what could be the best couple, right? We don't have to try them all, right? I mean, intuitively, maybe we need to try more than just these two, right? But they prove that we just need to try these two if we use information gain, right? Then so then the rest will be easy, right? Because we don't have to try so many, right? Okay. Yeah, so that's one thing. But I mean, that's the that's the simple situation, right? The real situation is like what? Right? So everything will be mixed. So you have to be a little bit clever to say how to choose, right? I mean, the real could be like this, right? Okay, suppose a blue one, white one is belongs to one label, right? Okay, and be like this, right? Okay, then maybe you have to try the bottom, right? So you really see this one as the blue and blue is blue, right? Maybe this is little one, you forget about that, right? Like what? Like okay, you consider what could be the couple. So you consider this one is the couple, this one is the couple, right? Okay, but forget about this, right? Because it kind of too small. Consider the noise, right? So maybe we don't forget about that. Yep. So that's the way to choose, right? Okay. So one thing is like this. Another thing we have to pay attention to is that given this continuous attribute, right? Something is not so fair. It's like, okay, for this kind of attribute, if we let them to compete with other attributes, right? In the information gain competition, right? Then this continuous attribute will be what usually will be favored because they got tons of them, right? So many in the pool, right? So they may be more likely to be chosen easily, right? That is up to you. You want this happen or you don't want, right? Okay, if you don't want this happen, maybe you can try some other way to downweight, right? But anyway, we'll talk about that in a few minutes. Yeah. So that's if we don't do anything, right? Usually the continuous attribute will be favored. So that's something you have to pay attention to. Okay. So here comes if we talk about we didn't talk about gain ratio, right? We gain ratio. Yeah. So here is something related to I just mentioned the continuous value could be continuous attribute could be favored, right? So then we talk about if the attribute with many values, would that be favored? Yes or no? The answer is yes. Okay. So if we come back to this, right? The outlook will have three values, right? The humidity, windy will be only two values, right? Okay. In this case, outlook usually will be favored. Why? Because given three branches, right? Down to the bottom, we will have what? Usually will have lower entropy, right? Okay. So some extreme case is that what? If we try the date, right? Remember, the data is like this. The data is like this one, right? if we only also consider date to be one of the attributes, which is not allowed, right? But just think about if accidentally that we include this one, right? Can we still have the right model, yes or no? Okay, the answer is that if we try information gain, then the date will be chosen because after we choose this date, right, everything down to the bottom will be just one no, right? So the entropy will be what? 0. So we must choose this one. So that's the best, right? But shouldn't be the best, right? So we need to find a way to penalize this situation. Give me a few minutes. So how to penalize? So we don't want to include attribute with many values. The there will be many values, right? Okay. So instead of using information gain, right, we use gain ratio. That's information gain divided by the split information. The split information is defined in this way. Okay. So we assume the after the branch, right, each will be a small region, right? Using this partition, we compute something like entropy again. Okay, so given this value, right, if we have so many branches, right, this split information will be very large, super large, right? Okay, and put it in the denominator will make the whole thing to be smaller, right? So they'll be unlikely to be chosen if we do have many values. Yep. So choosing gain ratio will be something to erase the multiple many value problem, right? And also maybe we can also deal with this one. Okay, maybe you can also deal with this one. Think about that. Say, I mean, if we only try binary, we cannot. But if we try this one with multiple branches, right? So this one maybe will be less likely to be chosen. Okay. We have a few more things, small items that let me finish this one. Okay. So this one is attribute with pose, right? So we can also consider for each of a different attribute, maybe, for instance, medical test, right? So they'll be associated with different pose, right? So why not to consider the cost to decide which one would be chosen, right? So then also we put the cost in the denominator, right? When the cost is large, then we could be less likely to choose this attribute. Okay, so I think it's not so difficult to understand. Unknown value meaning what? Meaning missing value. Okay, missing value. How to deal with missing value? So depends on missing in the training set or missing in the test set, right? If we talk about missing in the test set, okay, then what? Then it could be like we never use this attribute. Then that'll be fine, right? Okay, because we try to go from the root down to the bottom. Maybe we didn't try this attribute, so that'll be fine. Okay. How about if we try the value? Then what? First of all, missing value. How to deal with missing value? There'll be more than just one choices, right? Okay, so we can this. Should we finish? Do you mind if we finish this slide? Just this slide. This slide takes a while. Yeah. Anyway, I'll finish. Okay, you can go because they'll be recording, right? So you can check it later. Okay. Yeah. So missing value. I need to say the following: missing value is a big problem, right? Because when we have the data like this one, when we have a data, so that's the data, right? So if we have missing value here, there, right? So how to deal with missing value? First of all, you need to ask yourself: this missing is systematic missing or non-systematic missing. What do you mean systematic missing? Because they miss just because they don't want to declare. Then what? Then this missing means it should be some kind of like, okay, if maybe some of you got a vaccine, right? So, or maybe you go to the doctor sometimes and then they say, oh, they were going to ask you a lot of questions, right? Some people may tend to say no. You got that? Or if they don't want to lie, they just miss. They leave them as a blank, right? Meaning what? Meaning that actually it's yes, right? But they just don't want to feel, they don't want to lie. So that's why they don't want to feel anything, right? So in this case, missing means yes. So that's why we say systematic missing, right? Okay. Also, some a survey for politics, right? They try to ask their what kind of party that you favor, right? They also quite often that you will have a systematic missing, right? So for systematic missing, I mean that's up to us, right? If we know that systematic missing, then we feel something. I know it's kind of arbitrary, right? On the other hand, if it's not systematic missing, then we can do what? Proportional to whatever situation compared to some other things, right? So if we have this one missing, right? Then we check all others, right? To see if there's anything similar, what kind of value they have, we copy and pass, right? Okay. If it's not 100% the same, right? Then we do proportional, right? It's like that, right? So that's a way to deal with missing. Once that we try to fill them with values, that there's no longer missing, that we can continue, right? The same thing here. So if we don't try to fill them out, we can try something similar. We can try something similar, such as that we can, such as that if we have missing in the training, let's talk about testing first, right? If we have missing in the testing, then we can do things proportional. Like, okay, this value is missing, but the model asks for it, right? Then we can do it proportionally, right? Like how much percentage like should go to the left, how much percentage should go to the right. We do it probabilistically, then we try both actually with some kind of weight. And down to the bottom after that, we got the values, the label. We compute the label proportionally to see what would be the best answer, right? Okay, so that's for testing. For the training, kind of similar, right? So we can try proportionally, right? So given this missing, right? So we can say, first of all, do we need to check this attribute as one of the information gain computation, right? We can what? Choose to be ignore this data in the information gain computation. We can try proportionally, just like we fill some kind of value, right? Okay, just because we don't really ignore this data, right? So we ignore this data in the information gain computation could be not so big deal, right? So it depends on your choice, right? And what else? Okay, so I think we already cover all the things here, right? Like we talk about probability, right? Okay. Yeah. So that's all, right? So just one minute to finish this, right? So what you should remember for the entry, right? So it's the transparent model. Don't forget that, right? So it's always useful when we need some transparency, right? Okay. So then everything here in the entry will be super efficient, right? Training and testing will be very fast compared to all other models. Right? And when we need to deal with real world data, I think we still need some careful treatment like continuous value for missing value, right? All kinds of situation, right? Okay, and we can work with even we didn't talk about here, right? We can use a committee. Committee means a set of different several trees together, and also with voting, we can get not so bad result. And theoretically, people already, or maybe empirically, people already say that, okay, check the committee, meaning a set of trees, right? We compare to supervised machines, which was one of the best model, right? Then they do have some similar uh, similar effectiveness. Okay, so that means what? That means entry is not bad at all, right? In this sense. Okay, but remember, if we talk about a set of trees, right? It's no longer, it's kind of like a transparent model, right? If we have so many trees, right? Okay, it's not that easy to build intuition, right? But still better than deep learning model. Why? Because we can still manipulate the result. That's true, right? Given 10 trees, even 100 trees, we can manipulate for each of the tree to make sure that what kind of result that we have for each data, right? We can still do it, right? But we cannot easily do it for uh, deep learning model, right? Okay, that's all. Any questions? Okay, yeah. So tomorrow we start to talk about uh, networks. Yeah. Okay, so see you tomorrow. Bye bye. Bye bye.